Krasovsky of Imperial College, and he's speaking on, I think, almost messy operator.
Yes. Okay. So I'd like to thank organizers for invitation, and he will present you some of this, some of the results about this, the so-called almost messy operator. So we consider the some operator H on space of sequences, 2 of z, and it is given by the following equation. So if you apply to the vector of the space, then it is Cn plus 1 and minus 1, and the 2 lambda cosine. Okay. Right, so it is a discrete Schrödinger operator, say, because it is, well, it is 1, 1, and some diagonal term, which is a potential, right? So lambda, these are lambda alpha theta subparameters. We don't lose any generality if we assume lambda positive. Well, alpha and theta are real numbers. So this equation has a nice interpretation, physical interpretation. So this, in fact, it describes electron on a square two-dimensional lattice in a uniform perpendicular magnetic field. So if you would like to consider a particle on the lattice and magnetic field, this is the simplest possible model. Two-dimensional square lattice and a uniform magnetic field. So lambda is related to the anisotropy of the lattice. In particular, if lattice is isotropic, lambda is equal to 1. And alpha is related to the strength of magnetic field. So theta is, in a sense, auxiliary parameter. So in order to, the model of, this model corresponds to the direct sum of these operators over theta. So it turns out that along one dimension, you can diagonalize the model using Fourier transform. And so the non-trivial part will be like this. And the original model is the union of all theta, right? So this is the model. So now the model appeared already in physics in Piles, works of Piles, so it is really very old. It was investigated by various physicists, Asbel, Hofstadter, Harper. So in the 50s, 60s, and there is a famous picture of its spectrum, which is called Hofstadter butterfly. And the interesting thing is that the spectrum has very unusual properties. So it is a nowhere dense set for irrational alpha. And so this is because we have a competition between magnetic field and the lattice potential, if alpha is irrational. So if alpha is rational, this is periodic, and if alpha is irrational, it's quasi-periodic. And so this is the most important example of the general class of quasi-periodic Schrödinger operators. Okay, so so what features does this model have? And it has lots of interesting features. Well, first of all, first of it, it's related to localization-delocalization phenomenon. So if lambda is larger than 1, then the spectrum is usually pure points set. pure point but it's not always. So for Lebesgue, almost every alpha and theta. So a spectrum pure point also with exponentially localized eigenfunctions. So this is a regime of so-called localization. Okay. So if lambda is less than 1, then the spectrum is absolutely continuous for all irrational alpha and rational as well, of course. So it is spread, so like the Bloch waves. So in this case, so generalized eigenfunctions, they're not localized. This is delocalization. So and the case of the isotropic lattice corresponds to the transition between the two. And here is spectrum singular continuous. Well, this is a transition between localization and delocalization. And also this is the most important, most interesting parameter here, as we will see. So now, from now on, so let us focus on the structure of the spectrum as a set. Spectrum as a set. So let's denote it sigma of h. Sigma of h. So we will also look at the measure of the spectrum, a Lebesgue measure of the spectrum. So let's call it like this, sigma of h. That's a Lebesgue measure. Okay. So what can we say about the spectrum? So let us note that if alpha is rational, P over Q, then sigma of h consists of Q intervals. It's just Q intervals on the real line. Q intervals on the real line. So note that this potential is bounded, so it will be on some unbounded interval. So this is on a bounded set. So set is bounded and consists of Q intervals. Okay, so if alpha is, if Q grows, the number of integrals grows, intervals grows. So if alpha is irrational, the question is, what does the spectrum look like? This is a well-defined set, but what does it look like? And this will be subject of the next theorem. But before that, let's note that, in fact, if alpha is irrational, then the spectrum does not depend on this parameter theta. So if alpha is rational, then the spectrum, as I said, does not depend on theta. If alpha is rational, it does depend on theta. So the Hofstadter did numerical simulation, and he plotted the plot of the spectrum as a function of alpha. And this looked like a butterfly. And so since then, it was known as a Hofstadter butterfly. You can find it easily on the web and have a look how it looks like. So related to that is the following theorem, which says that so that for any rational alpha, and of course real theta positive lambda, sigma of h is a Cantor set. So I will remind you what that means. So the Cantor set, just by definition, is a closed nowhere dense set. Set without isolated points. Okay, so the most important point is that it is nowhere dense. And also, it has an explicit measure for 1 minus lambda. So this theorem was a result of work of many people, and I will give you a brief history of the proof of this statement. But let us note for future that for the critical case, lambda equal 1, so this I will call a critical case. So if lambda equal 1, the spectrum has measure 0. So the measure of the spectrum is 0 according to this theorem. And from here, it immediately follows that it is a Cantor set. It is just straightforward, and therefore Cantor set. If lambda is not equal to 1, it has a positive measure, and the fact that it is a Cantor set is non-trivial. So one has to prove it separately. Right, it could be. But for 0, 0 immediately follows that this Cantor set. Okay, so yes, so this theorem, some of the statements of the theorem were known for some time as conjectures. So the measure of the spectrum, this is so-called Aubry and Andre conjecture. And the fact that it is a Cantor set, it is known as a 10 Martini problem. So in 1980s, when this operator started attracting attention, it was Mark Katz who offered 10 Martini for the solution of the conjecture that the spectrum is a Cantor set. And then, some years later, Barry Simon started calling this problem 10 Martini problem, and since then it is known by this name. So this is okay. So what was the progress towards the proof of the theorem? It was proved in many steps over many years. So the main, maybe I will give you some main developments. So maybe the first was that C of H is a Cantor set for a dense set of pairs. Lambda alpha, but not specified on R2. So this was done by in the work of Billy Sarden Simon. In 1982. So then it was noticed some years later that for Liouvillean irrationals, sigma h is a Cantor set. So Liouvillean means that it is very rapidly approximable by rational approximates, exponentially rapidly in the denominator of a rational approximate. So this is well approximable irrationals. So this is a Cantor set. This was done by Choi, Elliott, and Yui in 1990. Yes. Okay. So then there was a very big progress. So namely, the fact that the measure of the spectrum is equal to 4, 1 minus lambda was proved by Last. So in 1993-94, but not for all lambda, but not for all alpha. For almost every alpha. So namely, alpha of so-called unbounded type. So it means that the q times the root alpha minus p of q should tend to 0 as p of q approximates our irrational number. So this property approximation by rationals is true for almost every irrational, but not for golden mean. As we saw last previous talk, we had a golden mean. So for golden mean, this is not true, so because it's badly approximable. Okay, and so the question actually remained how to show it for all irrationals, and that proved to be a difficult thing to extend, because they relied on some continuity estimates which did not which was not strong enough. Well, I will tell you later maybe what it was for the estimate. Okay, so then actually we managed 15 years ago with Svetlana Jitomirskaya to prove the result for the measure for lambda not equal to 1. So the fact that sigma h is equal to 4, 1 minus lambda not equal to 1. So that was our result. In 2002. And this was true, and we proved it for all irrational alpha. Because in that case, when lambda is not equal to 1, you have better continuity estimates. But the critical case lambda equal 1 remained open. So that was done finally in the work of Avila and Krikorian. So the fact that sigma of h is equal 0 for lambda equals 1 was done by in 2006. From here, as we noted above, follows Cantor structure of the spectrum in this critical case. So they did this by methods of dynamical systems in a rather complicated way. So for some class of Diophantine alpha. Diophantine means that it is very badly approximable by rationals. So it is an opposite Liouvillean, and Diophantine is opposite properties of irrational numbers. Diophantine are very badly approximable, but this set for which they did it together with the result of last, if you put them together, it covers all irrationals. So that the proof was for Diophantine, but sort of this completed the proof for all irrational. So completes the proof for and lambda equals 1. Okay, to give you a complete picture, what remains to prove here, it remains to prove the Cantor structure for lambda not equal to 1, right? So, because from here it doesn't follow that it is a Cantor set. Yes, and so for lambda not equal to 1. So it was an observation of Push, which actually preceded preceded this this done 2004. So he observed actually that sigma of H is a Cantor set for Diophantine alpha. But it is still did not finish the full proof, because we had now for lambda not equal 1 this Choelet new found it for Liouvillean, here for Diophantine, and there was still something in the middle not covered by these two results. And so the final answer was done by in 2009. So Avila and Jitomirskaya. So they completed the proof for lambda not equals 1. Okay, so this is the history of this theorem, and so now so one of the results that I would like to talk about today is that actually recently we found a new argument. And in particular, this argument so far works only for critical case, lambda equals 1, but it gives a very easy elementary proof of the theorem in this case. So we obtain. So I mean myself with Svetlana Jitomirskaya. So I knew an elementary proof. That sigma of H is 0. So measure is 0 for all irrational alpha for the critical case. So, and then from now on, we will only discuss this critical case. Lambda equals to 1. Well, in fact, we had two different new proofs, both of them elementary. Okay, so in fact, our method allowed us to find a stronger result than just zero measure, and namely to say something about Hausdorff dimension of the spectrum, right? So the question, of course, once you found how can you study the spectrum further? So once you have found the measure is zero, the next natural question is what is the Hausdorff dimension, right? So this is the next natural question. So what is Hausdorff dimension of the sigma of H, sigma of H. Yes, what is the Hausdorff dimension of the spectrum? So let me remind you the definition of Hausdorff dimension. So first of all, you define a Hausdorff measure of the set A. So suppose A is a set on the real line. So then you define a so-called Hausdorff measure. So this is the limit when delta comes from above to 0. So infimum over all delta coverings of the following sum, Wj so j from 1 to infinity. T is some parameter. Yes, and so what is a delta covering? Is that A should be covered by the union of omega j's, omega j interval, and the measures of all this omega j's is less than delta. So it's a countable covariance by intervals of small measure. So so if you look at this at this object as a function of t, so you see that if you take t is sufficiently large, then this one, because this goes to 0, so if then the whole thing will be 0. And if you take t is sufficiently small, rather small, then the sum will diverge, it will be infinity. So, and indeed, if you plot the graph of this with t, then it will be 0, 0, then it will be jump at some moment, and then be infinity. So the moment when this jump happens is called the Hausdorff dimension. So dimension Hausdorff dimension of A. So this is the infimum over t such that measure of A is finite. Well, 0, but it's at the point of the jump it can be finite. Yes. So this is a definition. Okay, so now let me tell you a bit of a history. So the question was actually posed by Thouless, by David Thouless, in the 80s. So he investigated numerically a lot and also analytically this model, and observed numerically. that for the rational case, P over Q, the measure of the spectrum is small. So it behaves as some constant divided by Q, for large Q. So this is already an indication that in the limit you have zero measure, but of course this is a very bad object in terms of its continuity, and you don't know if it is continuous, and it definitely discontinuous at all rational points. So, but at irrational it is continuous, but it requires a proof. Okay, so he observed that this is true. So then if all Q intervals of the spectrum in this case were to have the same length, this is actually, I should tell you, it's not true in reality. So because some of them are exponentially small in Q, and some of them only polynomially small in Q. But if they were to have the same length, then they would be of length of course 1 over some constant divided by Q squared. So Q of them, right? So, and this gives a very nice indication of the fact that Hausdorff dimension should be 1/2. So, so one can conjecture that the dimension Hausdorff of the sigma is actually equal to 1/2. But indeed, if you apply this definition, then suppose that the intervals of periodic approximants approximate them very well, then you will have to consider the sum from 1 to Q. Each interval will be of order 1 over Q squared, and then you put it to some power Ts over there, and then see what happens with this when Q is large. Right, so then you see that it is basically Q times, because if they have the same length, it is Q times. So if T is 1/2, it is exactly the case when you have something finite. T is larger than 0, and if smaller, it goes to infinity. So 1/2 should be a Hausdorff dimension. Everything goes right. So there's no problem, if there were no problems here. So, however, this kind of a rough result is not, turns out it is not always true. So it turns out that, so in fact, so there exists some Liouvillean alpha such that the dimension h of sigma is equal 0. So this was a relatively recent result by Last and Shamis, 2016. But also there are some Diophantine alpha such that this dimension is strictly positive. Dimension is strictly positive. So, so what is the answer? Well, there is another conjecture that the dimension is the same for almost all alpha. And also there is a result of Last which showed that for some so measure 0 set of alpha, this dimension the dimension of sigma is less or equal than 1/2. So that was shown by Last in 1994. Right. And so, this is the question. So what our results allowed us to do is to prove this fact for all irrational alpha. So in fact, it is if you look at the original conjecture, you can ask if you can interpret it as two inequalities, one direction and the other direction, and then it means that well, at least it is not larger than 1/2. So we have the following theorem. So our Svetlana theorem, which we proved this year actually, that for all irrational alpha real theta, this dimension okay, is less or equal 1/2. Say 1/2. Okay, so and yes, so this is the mystery which remains is just to see if this is true that it is the same for all almost all irrationals, and what is the value, right? So now let me maybe give you some ideas of the proof. Okay, so the first idea was the following: we observed that there exists certain unitary transformation, which actually, if you apply it to the original almost Mathieu operator, brings it to a different but much nicer form for us. So there exists unitary transform that shows that actually, if you take the spectrum of operator H at some 2 alpha, right? So and take the union of all thetas. So then it will be the same as union of all thetas of our operator, somewhat different operator. And so this different operator acts in the following way. So remember, it was 1 phi n plus 1, 1 phi n minus 1, and the 2 cosine in the middle, right? So now there is no middle term. Middle term is 0. And we have a 2 sine 2 pi alpha n plus theta phi n minus 1, right, plus 2 sine 2 pi alpha n plus 1 theta phi n plus 1. Right, so there is no there is no middle term here, but instead of ones and of diagonals, you have this oscillating sign. So in fact, before I tell you why it is so nice, maybe I should give you just general form of what is this transform. So first of all, this transform So is interpreted as it's a so-called gauge transformation of magnetic field. So it uses the fact that problem is two-dimensional in a non-trivial way. That original problem is two-dimensional. It's two-dimensional. That's why it does not transform you the spectrum of for each theta into another theta, but only union over thetas. So it mixes up the phases also in this transformation. So this, the fact that this transform exists was known to physicists actually and to us as well in the 90s already, but somehow, so we didn't know how to use it properly, and we didn't know how to prove this rigorously as well, because in physics it's a bit non-rigorous. One can find a nice argument for a rational case, but for irrational case it was not immediately clear, and so because we didn't know how to apply this, it was sort of unused, but now we realized how to do this, and so this transformation, maybe I will write roughly how it looks like. So it looks very roughly in the following. There are some constants which are not important, and k, sum over k plus k squared plus k theta plus c5 n beta, and here is an integral integral is before this. Let's put it here. Phi k beta, e beta. So what does it? This phi and theta is corresponds to the space with. So you remember that the regional space was divided into direct sum over thetas. So so this phi n is a vector for some particular theta. For some particular theta. And so the transform uses some kind of integral over all the thetas, but this part is quite interesting because there is a quadratic polynomial in exponential. It reminds somewhat about theta functions and maybe Gauss sums in the discrete situation. Yes. So roughly speaking, it is something like this. So now, why is it actually so interesting? So it is interesting because the off-diagonal elements are sometimes very small. Because sign vanishes, right? If it is close to 0 modular n, then it is 0, and so it means that the matrix quasi-separates into blocks. So so H hat into blocks, which has a lot of lots of very important properties. So in this case, from here one can already prove the fact that the measure of the spectrum is 0, because if it has this property of this quasi-separation into blocks, So it is known that if you, for this type of tridiagonal matrices, they cannot have absolutely continuous spectrum. So H cannot have absolutely continuous spectrum. But on the other hand, also called Lyapunov exponent, in this case is a 0, so which I don't have time to explain, but you know, there is, you associate with this matrix Lyapunov exponent, showing you how fast the eigenfunctions grow. And in this case, they practically don't grow, and you know that the exponent is 0. And then there is a so-called Catani theory, which tells you that so that if the spectrum were to have a positive measure, then almost everywhere it should be absolutely continuous. But it is not possible because it quasi-separates into blocks. So the absolutely continuous spectrum is not possible. So by this very general argument, it already follows that absolute value C of H is 0, so measure is 0. But there is more direct proof also. This is not sufficient to show the Hausdorff dimension property, but the next observation is sufficient. So the fact that the H quasi-separates into blocks implies that so therefore one can obtain improved continuity for the measure of the spectrum. And improved continuity of the spectrum implies this result for Hausdorff dimension and also for zero measure. So which implies the theorem. Yes. So how does it imply the theorem? So there is rather a simple argument by Last how does imply the theorem. But the difficult point was to prove the this continuity result. To prove the continuity result. So one does. There is already some indication from here that such continuity can be improved. But we run into a certain difficulty, and it took us some time. And in fact, the thing which actually in the end resolved this difficulty is the fact that the properties of this sphere, when you look at them, in the following way of eigenvalue equation. So then phi of E, phi n of E are orthogonal polynomials. And the measure of orthogonality is exactly the spectral measure of the separator, which lives in a Cantor set. But orthogonal polynomials, they can be normalized. In fact, orthonormal polynomials, we have the following property that that integral with respect to the measure is equal to 1 for all n. The normalization property of orthogonal polynomials, and which means that they cannot be very large at the points of the spectrum, because otherwise this will be violated. And the fact that one can control their size allows one to improve continuity of the spectrum, from which one can use immediately the argument of Last to finish the proof. So this is very roughly in a few lines. So these were two main ideas. So one is this, and the other one was a control on the size of the of this. But and there was a third ingredient, which is a certain argument, certain approximation argument. We use the special value of theta, where these things are really very small. So there are some thetas where on a sequence of n's they can decrease as very, very quickly, and there is some tricky way how to choose this theta. So there were three main ingredients. Okay, thank you very much.
Why cannot we use this relation to orthogonal polynomials from the very beginning?
Which one?
Just, I also can think about almost Mathieu equation as a three-term derivative.
Yes.
So why? Okay, so what?
Because I didn't tell you the whole story, there was not enough time. But in order to prove this continuity, one has to find some cut-off solutions. Some solutions you cut off at certain points, and the points when you cut them off should correspond to the places where this thing is small. Okay, so and this minimizes the error. But the problem is that the error is a product of this and this. It's a product of this and this, the error. And so not only this should be small, but also this should not be too large. Well, in a regional setting, this is just one, so it's never small. It doesn't help. And here it helps only because we have this additional prefactor. Yes, this is kind of how it works. Yes.
If you consider this as difference equations with variable coefficient, the original one, would it help to formulate the theory of the existence uniqueness of difference equation? I mean, the original operator you had, right, put f, there is no function in the right, forget about the operator, and consider it a separate difference equation with variable coefficient.
Which f?
F, anything. I mean, again, you have in the first, the beginning you wrote your operator, right?
Yes.
Somewhere.
I deleted the original. Yeah.
Anyway, forget about the operator. We put some known function f of n and consider it as a difference equation for arbitrary n. Right? If that middle term coefficient is not cosine multiplied by something, but just a constant, it can be easily solved because it's just.
If coefficients are constant, yes, it's just.
Variable coefficient like yours, for instance, then there is no exact solution. Would it be possible to write, in some sense, a general theory of existence and uniqueness solution to such?
Well, there are some quite a lot of results on difference equations, various types, but no. But okay, so if it gave something, we would use it, right? So I guess. So you have to use something. You have something specific for this, which is true for this one. And this one does have some elements of solvability in it, but it is not exactly solvable on the other hand. Yes, but nevertheless, it's much better than the general case because there are some properties. For example, this.
I have another kind of this equation. So what about the Riemann-Martini problem?
Yes, it is. I think it's still not done. Yes. Yes.
Anybody consume Riemann-Martini?
Well, who will offer it now? Unfortunately, who will now offer it? So this is the question. Otherwise, Lana might well, although she wouldn't probably like it.